Let's discuss about the cathodic protection. There is a group discussion between lead engineer, corrosion specialist, and structural engineer, electrical engineer. All right, team, we need to wrap our heads around this corrosion protection system design using sacrificial anodes. So we are going to discuss about the sacrificial anodes. The client wants us to finalize the design, and we need to ensure everything is in order. And any thoughts on the first step? So first step is going to be the surface area calculation. Surface area calculation, right? So the first thing we need to do is to calculate the total exposed surface area of the structure. We are talking about breaking the surface into zones like a splash zone, submerged zone, and buried zone. So first step is to calculate the total exposed surface area of the structure, and we are talking about the breaking the surface into different zones. And yes, that's right, but how do we handle the complex structures? Suppose if you have complex structures, for instance, should we be calculating surface area for components like jacket, leg, brace, conductors, or those operators? Good point. So the surface area of each zone has to be calculated carefully, especially for the complex structures. If we don't have the exact details of the connected items early on, we'll need to factor in an expected increase. Suppose if you don't get the exact details on the connected items, then we need to factor some additional or expected increase. We need to factor in the expected increase. We may also need to include temporary items like construction equipment or conductors during installation. Hold on, I'm curious, how do you handle the piles, specifically outer surface of below the seabed level? So how do we handle the piles, especially outer surface of the file below the seabed level? I mean, you have to get in. We have got to account for the submerged and the buried zones, right? So in the buried zone, we need to see it. For the piles, you calculate the outer surface area below the seabed level and consider it in the submerged zone. So we need to consider that in the submerged zone. If there's a score around the pile, though, that exposed area goes into the submerged zone too. But once we have the surface areas, what's the next step? So first we calculate surface area. Once we have the surface areas, what's the next step? Next step is how do we determine the current demand? That's where the current demand calculation comes in. That's where it comes in. We will use those surface areas and design current densities for each zone. So for each zone we have different current densities. So each zone we have the surface area and design current densities. We got to account the coating breakdown factor in the splash zone also. We have to account the coating breakdown factor also. So let's see, like, the design procedure for corrosion protection system means first step is to calculate the surface area, right? Let's see, the section outlines the systematic approach for designing corrosion protection using the sacrificial anodes, which offer electrochemical protection to structures exposed to seawater. So what is doing? It offers some electrochemical protection. The system is designed to ensure the sacrificial anodes corrode instead of the protected structure. So system is sacrificial anode system. In this one, the anodes, sacrificial anodes corrode instead of uh, protected structure. That's where it is designed. System is designed, preserving the integrity of the structure over time. So the structural integrity is preserved over time. Objective is nothing but the purpose of this step is to calculate the surface area of the structure exposed to seawater, which is crucial for determining the number of sacrificial anodes. So surface area is the crucial factor that determines the number of sacrificial anodes required. The amount of the current that must be supplied by the sacrificial anode is directly proportional to the exposed surface area of the structure. So that's one thing is clear, like if the surface area is more, it's directly proportional to the number of anodes, the amount of current that must be supplied by sacrificial anodes. So sacrificial anode purpose is it's going to supply some anodes. The amount of that current that must be supplied by anodes, sacrificial anodes, is directly proportional to the surface area to be exposed surface area that to be protected. The larger exposed surface area requires more anodes. For complex structures, the surface is divided into smaller zones depending on the exposure seawater, such as splash, submerged, and buried zone, as well as the presence of coatings and temporary components also. The total surface is calculated by summing up the exposed areas of all relevant components: jacket, leg, brace, wires, connectors. The structure is divided into zones to account for varying water exposure levels. Each zone surface area must be calculated separately. So what are the zones? Splash zone, submerged zone, and buried zone. The splash zone is nothing but the area exposed to both air and seawater. Usually both air. Splash zone is nothing but that's exposed to both air and seawater. Submerged zone are the underwater area that's below the splash zone. Buried zone is a portion of structure buried below the seabed. That's buried below the seabed. The next thing is design current demand. To calculate the electrical current required from sacrificial anodes to achieve the polarization and prevent corrosion of the structure. So what's the objective? We need to calculate the current demand. Current, not current demand, totally a total electrical current required from sacrificial anodes to achieve polarization and prevent corrosion of the structure. Physical explanation: if you the required current for corrosion protection is determined by the size of the exposed surface area and environmental factors. Different zones have different current densities. This is very important. Different zones have different current densities, which depend on factors like seawater salinity, coating condition, any additional items that connect to the structure. For the splash zone, we can say that I naught equal to S0 into I naught, small I naught into FO. For a submerged zone, S naught into I naught. For zones below submerged zone, I naught is nothing but S naught into IO. Number of conductors in current drain. This is important. Number of conductors and current drain. That's something additional for the buried zone. Number of conductors and current drain. S naught is the surface area of the respective zones. I naught is the design currents and current density for each zone. F naught is the coating breakdown factor. Current drain accounts for additional current needed for conductors. Current drain is nothing but the additional amount of current needed for conductors. This calculation ensures that the correct amount of current is provided to protect the structure in each zone. So we can say that correct amount of current is provided for to protect the structure in each zone. The next is annual dimension calculation. To determine the dimension and weight of sacrificial anodes need to provide sufficient current throughout their life. The sacrificial corrodes over time, right? Which means it dimensions change as it degrades. So sacrificial anodes is going to corrode over time, right? That means its dimensions changes and it degrades. It's important to account for both initial and final dimension of the anode to ensure it remains effective throughout its life. So we have to see whether it's going to be effective throughout its life. So we have to see, consider both. We have to account for both the initial as well as final dimensions of the anode. Initial and final dimensions of the anode. For non-cylindrical anodes, the approximate equivalent radius is calculated to represent anode's lateral surface and volume. Lateral surface area we can calculate using this one, and mass and volume representation also we can see. And weight calculation. Weight is nothing but W final is nothing but WA into 1 minus U. WA is the anode's initial weight. WA is initial weight and W final is the final weight. U is the utilization factor, fraction of anode's material effectively used. And that's utilization. This step ensures anode is sized appropriately to deliver the required current over its service life. So, alright team, we have been tasked with designing corrosion protection system using sacrificial anodes. We have been tasked with designing a corrosion protection system. So to make sure we are on the right track, we need to break down the key formulas and understand the physical meaning. We'll start with the surface area and move through all the steps. Okay, let's dive in. Great. First, we need to calculate the surface area exposed to seawater. This is crucial because it determines the current demand that anodes will need to supply. So first step is to calculate the surface area that determines how much current, the current demand that anodes will need to supply. More surface area requires more current. More surface area requires more current. We calculate the current demand for each zone in this formula. We know this current demand for this particular zone, and S0 is the surface area exposed to seawater of that zone. I naught is the current density, the amount of current that flows per unit area. Current demand is the how much current needed that has to be supplied by anode. That's but current density is nothing but how much amount of anode can flow, current can flow per unit area. F naught is nothing but the coating breakdown factor, accounts for the protection the coating provides. So the more surface area exposed to seawater, the higher the current demand. More surface area exposed to seawater means higher the current demand. And if the coating is damaged or ineffective, we need to factor in F naught, right? If coating is damaged or ineffective, we need to factor in that. That's why if your coating is damaged, it will have more factor. If the coating is intact and effective, FO would be lower. If it is intact and effective, FO would be lower. So current demand will be less. If it is damaged, then current if it's damaged, we need more current to protect the structure. If it's damaged, more current we need to protect the structure. Got it. But once we calculate the surface area and current demand, how do we figure out the size of the anodes? Once we calculate the surface area and current demand, how do we figure out the size of the anodes? Good question. To size the anodes, we need to calculate the resistance and current output. We need to calculate the resistance and current output, how much current output is going to be and how much resistance is going to be. Now let's look at the resistance. Right, the resistance of the anode depends on the material property and dimensions also. We calculate the resistance using this formula. RA is the resistance and rho is the resistivity of seawater, L is the anode length, and A is the cross-sectional area of the anode. So if the anode is long, it will have higher resistance. If anode is long, if it is anode is long, it will have higher resistance. Length is more, resistance also more. And if it has a larger cross-sectional area, if it has a larger cross-sectional area, then it will have lower resistance. Area is more, then resistance will be lower. It will have a lower resistance. If it has a larger cross-sectional area, it will have lower resistance. A longer anode increases resistance. If longer anode increases resistance, it makes it harder for the current to flow through it. Why? Because it makes it harder for the current to flow through it, because it's more length, it has to travel more length. That's why it makes it harder for the current to flow through it. If the larger cross-sectional area allows more current to flow, reducing resistance, and the cross-sectional area is more, it will allow more current to pass through. It allows more current to flow. That means it's reducing the resistance. So area, if it is more, it's reducing the resistance. If length is more, it's increasing the resistance. So we need to play with the dimensional characteristics of the anode. So after we calculate the resistance of anodes, we can determine the current output. Output is nothing but the E driving. We can use the Ohm's law. That's E driving divided by RA. Current output. We can calculate the current output. Current output is IO. IO is the current output of the anode, and E driving is the system's driving voltage. The difference between the designed potential and the anode's closed circuit potential. Difference between the designed potential and anode's closed circuit potential. RA is the resistance. Ohm's law. This is the Ohm's law. If potential is more, you will have more current. If resistance is more, you will have less current. So potential is nothing but how much current available times resistance. That's the potential you can calculate. So higher resistance means the current output will be lower. If resistance is higher, your current output will be lower. If resistance increases, anode will provide less protection. If resistance increases, anode will provide less protection. That's correct. That is why we need to ensure the anode is on the of the right size and material to minimize the resistance while maximizing the current output for adequate protection. Now we know how to calculate the current's output. How do we figure out how many anodes we need? We know current's output. We know how to calculate the current's output. How do we figure out how many anodes we need? How do we figure out the anodes we need? We calculate the total number of anodes needed by dividing the total current demand by the current output. IO is the current demand and IA is the current output. This is anode output. This is the demand. So we can calculate the number of anodes by dividing the current demand by current output of a single anode. This is a single anode's output. So n is the number of total anodes required. Total number of anodes required. Current output from all zones. This I naught is nothing but from all the zones. Current output from one anode. So if we need more current protection, we just add more anodes. If we add more anodes, we will have more current protection. But we also need to check if the current output is enough for both initial and final conditions of the anode. We need to check for the initial as well as final conditions of the anode. Actually, we need to ensure that anodes will still provide the current as they deplete over time. They are going to deplete over time, but even after depletion, it should be able to provide enough current. Okay, but how do we know the anode is effectively protecting the structure? We have to check the polarized cathodic potential. How do you know the anode is effectively protecting structure? We have to check the polarized cathodic potential. What's that exactly? The polarized cathodic potential is nothing but potential generated by anodes that ensures that the structure is protected from corrosion. We calculate it using the formula I naught RA by N plus E closed circuit. Polarized cathodic potential, I naught total current demand, anode resistance, number of anodes. Closed circuit potential, the anode potential when there is no external current. When there is no external current, what is the potential? So the more the anodes we have, more current we can provide, which increases the potential, ensuring the structure is protected. And closed circuit tells us the baseline potential of the anode when it's not connected to the system. Baseline potential of the anode when it's not connected to the system. Exactly. If the polarized cathode potential is within the required limits, we know the anodes are providing sufficient protection. If it's too low, we need to increase the number of anodes of their size to boost protection. And finally, as the anodes deplete, we have to account for their resistance increase over time. How their resistance increase. Finally, if the anode depletes, we need to account for how the resistance increases over time, which will lower the current output. That's why we need to say the final conditions of anode to write. So we need to check for the final condition also, because once it gets depleted, it will the resistance it might be increasing. How the resistance increases over time, which will lower the current output. If it increases, if there is increase in resistance, it will lower the current output. So yes, we need to consider both initial and final conditions to make sure the system continues to protect the structure throughout the anode's lifespan. The anode's resistance increases as it corrodes, which reduces the current output, but designs would ensure it still provides sufficient protection. To sum it up, the resistance of anode affects how much current it can provide. The number of anodes is based on the total current demand. Polarized cathodic potential ensures the system is protected, and all these formulas are interconnected to make sure the design is a reliable system. By understanding the formulas and their physical meanings, we can design effective corrosion protection system that lasts for years and keeps the structure safe from corrosion. What is the purpose of calculating surface area for corrosion protection system? So, what is the purpose of calculating the corrosion surface area for cathodic corrosion protection system? The surface area calculation is essential for determining how much of the structure is exposed to seawater. Surface area tells us how much of the structure is exposed to seawater, and this directly influences the amount of current needed to protect the structure. The more surface area exposed, the more current is required to prevent corrosion. More structure is exposed, more surface area exposed. More surface area exposed, more current is required to prevent corrosion. What zones are typically used when calculating surface area for calibration? Zone 1 splash zone. That's the area exposed to seawater during high tide and wave action. See, that's exposed to high tide and wave action. Area exposed to seawater. Submerged zone is nothing but the area below splash zone and but above the seabed. Buried zone is nothing but the area below the seabed, including the parts of the structure that are buried under sediment. How do you calculate the surface area for complex structures like jacket and piles? For complex structures, the surface area is broken down into smaller units based on the components like jacket, leg, braces, supplements, etc. and they are exposed to seawater. The exposure to seawater profiles, outer surface area below the sea level is calculated for the submerged zone, and part that is buried is considered in the buried zone. Outer surface area below seabed level is calculated for the. Okay, what factors should be considered when calculating surface area for connected items? Details are unavailable, and the estimated factors should be applied to account for an additional area that will be exposed to once the details are known. The temporary items like connectors, construction equipment also need to be considered during installation. What should be included in the surface area calculation for mudmat plates? Exposed surface is part of the submerged zone, while the surface resting on the seabed is considered part of the buried zone. The area that is that's resting on the mudmat, resting on the seabed. The mudmat area that's resting on the seabed is considered part of the buried zone. The exposed surface to seawater is considered part of the submerged zone. Current demand constant. What is the formula to calculate the current demand for each zone? That's nothing but I naught into I naught equal to S naught into I naught into F4. I naught is the current density, F naught is the coding breakdown factor. What current density values are typically used for different zones? Current density values used for based on zone exposure and environmental conditions. Splash zone usually require higher current density, 0.3 ampere per meter square. Usually the splash zone requires a higher current density also. Higher current density, splash zone requires higher current density. Submerged zone moderate current density, buried zone often lower or excluded unless specifically required by the project. How is the coating breakdown factor in this process? The coating breakdown factor is used in the splash zone to account for protective effect of any coatings. Protective effect of account for the protective effect of any coatings. If we are applied some coatings, what's going to be the protective effect of that coating? That needs to be accounted. That's how this coating background comes into play. Yes, if the structure is coated, this factor compensates for any loss of effectiveness due to the coatings wear degradation over time. This factor compensates for any loss of effectiveness due to coatings wear or degradation. What would happen if we didn't factor the coating breakdown factor? coating breakdown in the splash zone. If the coating breakdown is not factored in, the system might overestimate the effectiveness of the coating. If you don't consider the coating breakdown, it might increase or overestimate the effectiveness of the coating, leading to underestimation of the current. How does the surface, the current demand for the submerged zone and current demand for splash zone differ each other? The submerged zones does not require coating breakdown factor and is usually exposed to lower current densities. Submerged zones are usually exposed to lower current densities because due to the more consistent immersion in seawater. That's going to be always immersed in seawater, more consistent immersion in seawater, more consistent immersion. But in the splash zone, on the other hand, experience a more aggressive exposure and higher currents. It demands more higher current density because it's of its nature. It's going to experience more aggressive exposure due to tidal and wave action. That's going to be exposed to it, more aggressive exposure due to tide and wave action. Why do we need to calculate the dimensions of the sacrifice anodes? Calculating the dimensions of the sacrifice anodes is crucial because the size and shape of the anode determines how much current it can generate. Size and shape determines how much current it can generate. The right dimensions ensure the anodes provide adequate protection over the design life. How do we calculate the equivalent radius of non-cylindrical anode? We can calculate the equivalent radius of the non-cylindrical anode using this formula. How do we calculate the radius if you are representing the mass or volume? That can be done like this. What is the purpose of using anode utilization factor? Anode utilization represents fraction of anode's mass that is actually consumed during its service life. Okay. Utilization factor represents the fraction of anode's mass that is actually consumed during service. So actually it's consumed during its service life. This factor helps in estimating the remaining mass of the anode after corrosion. Okay, how much mass is going to be there after corrosion? Ensuring that the system is designed for long-term protection. How much mass is actually consumed during service? 95 if you put, that means 95% of mass is going to be consumed during its service life. 95 if you put, it is going to be good. How do you calculate the final weight of the anode after it has been depleted? How do you calculate the final weight after it has been depleted? The final weight is nothing but the initial weight into 1 minus 0.95. 1 minus 0.95, suppose utilization is 0.95, 95%, that means 0.05. It's very less, only 5% of final weight is going to be there. This formula estimates the remaining weight of the anode after corrosion. Anode resistance calculation. What is the formula for calculating the resistance of sacrifice anode? The resistance of sacrifice anode can be calculated using this formula. Re is resistance and rho is the resistivity of seawater resistivity. L is the length of the anode, A is the cross area. How does the seawater resistivity affect the anodes? If the seawater resistivity is directly influenced the anode resistance, higher the seawater resistivity, higher resistance, meaning anode will generate less current. If the resistance is more, it means that anode will generate, it will supply less current, right? Therefore, it's crucial to account for the seawater resistivity, the calculation. How does the seawater resistivity affect the anode's resistance? So it means seawater is going to affect the anode resistance. If the anode resistance is getting affected, its ability to generate the current output will be reduced. So that's crucial to account for the seawater resistivity in calculations. How does anode size affect these resistance? How does the anode size affect this resistance? The anode, larger the anode in terms of length and cross-section area, lower its resistance. This means it can deliver more current for a given potential difference, enhancing its effectiveness and burning. How is anode resistance affected with depletion? As the anode corrodes, its size decreases, leading to increase in resistance. So how is the anode resistance affected by its depletion? So anode is getting depleted over time. Because of the depletion, anode's resistance is getting modified, anode resistance is getting affected. How does it going to affect? If the anode corrodes, what's going to happen? As the anode corrodes, its size is decreasing, right? Its size decreases, so leading to an increase in resistance. That results in an increase in resistance. This must be considered in the design to ensure that anode continues to provide sufficient current as it wears down over time. What is the importance of calculating anode resistance accurately? What is the importance of calculating? Why is it important to calculate? Why is this important to calculate the anode resistance accurately? Accurate calculation of anode resistance is for determining the current output of the anode. So current output is completely depending on the anode's resistance. If the resistance is underestimated, the anode may not provide enough current for effective corrosion protection. What is the relation between the anode current output and anode resistance? What's the relation between the anode output and anode resistance? What is the relationship? It's indirectly proportional. The current output of anode is indirectly means inversely related to its resistance, according to Ohm's law. How do we calculate the total number of anodes? Total number of anodes is calculated by dividing the total current demand by the current output for the current demand for the structure by the current output of a single anode. IA is nothing but a single anode output. IO is the total current demand for the entire structure.